Hello everyone, welcome to my YouTube channel. So today I am going to discuss the problems from abstract algebra section of CSIR NET December 2023 paper. So I'll not write the whole question because it will take much time. So that's why I will just mention the question ID. Please match it. Okay. So the first question is that question ID number 704038. So let G be any finite group. Which of the following statement is true? Okay, so here you can see that the fourth one is correct answer. Okay, and I will give the counter examples for other. So how do I prove that the fourth one? So claim G is a union of proper subgroups if and only if G is non-cyclic. Okay, so how do I show that? First, so notation, observe Hg be the cyclic subgroup generated by G. Cyclic subgroup generated by G. Which is same as this one, right? Now if first let G is non-cyclic, okay, that means this is proper for any G. Since G is non-cyclic, the cyclic subgroup generated by G for any element G is always proper, because if it is not proper, that means cyclic subgroup generated by G is equal to capital G, which implies G is cyclic, right? So hence what you can do, consider G to be union of Hg. G belongs to G, which is same as union of cyclic subgroup generated by G. G belongs to G, right? Now the cyclic subgroup generated by G, this subgroup is always proper, and we can write G to be union of its proper subgroups, right? Okay, now conversely, let G is cyclic. Then we need to show that G is not union of its proper subgroup. So if possible, G is union of Hi belongs to some indexing set, okay, and each Hi is proper. Okay, since for some G, cyclic subgroup generated by G is equal to G, that means small g belongs to Hj for some j, right? So without loss of generality, assume j equal to 1. That means G belongs to H1. Means cyclic subgroup generated by G is contained in H1. This will imply H1 equal to G, because cyclic subgroup generated by G is itself is G, because G is cyclic. Hence H1 is not proper, implies H1 is not proper. That's a contradiction. Hence the 4 options are correct, right? Now by using this, fourth option is correct. Now by using this, we can do the other option. It is saying that if G is abelian, then G is union of its proper subgroups. Take G is abelian plus cyclic. Okay, take any Zn. That will be the counter example. Okay, the second one is G is union of proper subgroup if order of G has at least 2 distinct prime divisor. Take any cyclic subgroup with order of G has at least 2 distinct prime divisors, like Z6. Then it is not an union of proper subgroups, right? Because G is cyclic. and G is union of proper subgroup, that will be false in case G is cyclic. Hence fourth one is correct. Okay, now go to the next one. Okay, so there is another one problem coming from field theory that I have made already the solution separately. You can go and check. Fine. And let's move to other one. Right, so this one is simple basic number theory problem. I am assuming it from abstract algebra. So n belongs to Z such that n is congruent to 1 mod 7 and n is congruent to 4 mod 7. So n is congruent to 1 mod 7 and n is congruent to 4 mod 15. Okay, so that means n is 15k plus 4. So n is 3 times 5k plus 1 plus 1, which is same as n is congruent to 1 mod 3. And again n equal to 15k plus 4 means n equal to 5 times 3k plus 4 means n is congruent to 4 mod 5. Okay, so hence option 1 correct, option 4 wrong. Okay, okay, now 3 divides n minus 1 because n is congruent to 1 mod 3, as well as from the given condition 7 divides n minus 1 as n is congruent to 1 mod 7. Now GCD of 3, 7 is 1. They are co-prime. Hence 21 divides n minus 1. Hence n is congruent to 1 mod 27. Okay, so third one is also correct, but second one is wrong. You can construct such example like take 64 and that will be the counter example for option 2. Hence 1 and 3 are correct answer. Okay, move to the next one. Okay, this one is a very nice problem. So the problem says that let G be a group of 2 by 2 invertible matrix with entries from Z mod nz. Basically G is equal to GL to Z9. The ID number is 704085. This is the ID number. So G is GL to Z9 and A, small a be the order of G, then which one of the following is correct? Now see, we know that we can find the order of GL to ZP where P is prime, but for P is non-prime we can't find the order in a direct way because that formula is not valid for for any other n unless it is P. Okay, so that's why it is important to do it in a different way. So it is slightly tricky. If you don't know, then it is difficult, but if you can think, you can just try. So we already know the order of some group which is inside this group. What is that group? That group is GL to Z3. Why GL to Z3 is inside GL to Z9? Because see, if I take any element from GL to Z3, that means the entries are lying between 0, 1 and 2, right? Each entry either 0 or 1 or 2, and we can think that same matrix as a matrix mod 9, right? So hence G equal to, hence we can take GL to Z3 as a subgroup inside GL to Z9, right? So we are by using that card, and we know the cardinality of GL to Z3, right? What is the cardinality of GL to Z3? That is 3 square minus 1 times 3 square minus 3. which is 8 into 6, 48, right? So by using that, we are going to find the cardinality of G. Okay, so let's define a map which is obvious map from G to GL to Z3. Any matrix go to A mod 3. That means if you take any matrix A, B, C, D here, map it to A mod 3, B mod 3, C mod 3 and D mod 3. Why this map is well defined? Because if any matrix is 0 here, that will imply that 9 divides A, 9 divides B, 9 divides C, 9 divides D, and so on. And that will imply 3 divides A, 3 divides B, 3 divides C, 3 divides D. That means 0 goes to 0, which implies that this is well defined, right? And clearly this is an homomorphism. You can just check, this is clearly a homomorphism by obvious choice, by definition. So by first isomorphism theorem, G mod kernel F is isomorphic to F of G. Now from definition, if you take any matrix in GL to Z3, you can think that same matrix inside GL to Z9 also. Hence, this map is onto. So F of G is GL to Z3. Hence, order of G is same as order of kernel F times order of GL to Z3. Now, how do I see the order of kernel? Right? How do I see the order of the kernel? So, okay, from previous case, I think I did some mistake here. You can't take 0 here because this map is not under addition, right? This map is under multiplication, so you can't take 0. In particular, 0 is not in G. So to show well defined, what you need to show? You need to show that if A equal to B, then FA equal to F of B, right? And that is quite obvious from the definition, right? Right. So that is quite obvious from the definition, because here particularly what we are doing, we are just giving some map from the elements of Z9 to elements of Z3. And if I take any elements from Z9 and give it to and send it to mod 3, then that map is well defined. Hence this map is also well defined. The argument I already gave here is slightly wrong, so please remove that argument and do the simple thing. So there is no problem. It is quite obvious that this map is a well defined. Hence we can find the cardinality since this map is onto. So order of G is order of kernel F times order of GL to Z3. Now how do I show that order of kernel F? So kernel F means F of A is identity, right? That means A mod 3 is identity. Now what are the elements inside Z9 that goes to 1 under this map? So 1, 4 and 7, these are 1 mod 7, this is congruent to 1 mod 3, and 0, 3, 6, this is congruent to 0 mod 3. So hence F of A, B, C, D is 1, 0, 0, 1. This will imply A belongs to 1, 4, 7, A and B, and C and D belongs to 0, 3 and 6, right? So the choice is 3 power 4, because choice of A is 3, choice of B is 3, choice of C is 3, choice of D is 3, so it is 3 power 4. So kernel of F has cardinality 3 power 4. So order of G is 3 power 4 times 48. So let's match the option. So option first one is correct and second one is also correct. So 1 and 2. Now move to the next one. So okay. So given that this is the problem 704088, this is a very basic problem from Galois theory. If you know the definition of Galois group and properties, then you can just easily solve it. So fx equal to x cube minus 2 and k be the splitting field of fx over q. So fx equal to x cube minus 2 and k is the splitting field of fx over q. So what is k? K is q adjoint 2 power 1 by 3 comma I. What is Galois group? Since this is Galois extension, so and Galois group of q 2 power 1 by 3 comma I is isomorphic to S3 over q. Is isomorphic to S3. Okay. First of all, from the extension degree, we can see that the Galois group has order 6, and since the Galois group is, and you can see that the Galois group is non-abelian, so it is isomorphic to S3. And it is not I, it is omega. Okay, q 2 power 1 by 3 comma omega, because what are the roots? The roots are 2 power 1 by 3, 2 power 1 by 3 omega, 2 power 1 by 3 comma omega dot omega square. Right? Because x cube minus 1 has root 1 omega omega squared. So this is, so splitting field for f over q is q adjoint 2 power 1 by 3 comma omega, and hence Galois group is S3. Right. Now Galois group of k over qw. So Galois group of k over q omega. Sorry, I misread something. Extremely sorry. So Galois group of k over q omega is first find the extension degree. So extension degree k q omega is basically 3, and since it is Galois extension, so Galois group must have order 3, which is isomorphic to Z3. Right. So hence 1 and 3 are correct. Okay. So this problem is follows from the basic result of Galois theory. I mean field extension and Galois theory. Okay. Let's move to the other one. I think this is the best problem from this group theory section. Okay. So what is the following? Which of the following statements are true? Okay. So first statement saying that the ID number question ID 704083. So let G1 and G2 be finite groups such that order of G1 and order of G2 are co-prime, then any homomorphism from G1 to G2 is trivial. So if from G1 to G2 be a homomorphism, then by first isomorphism theorem, G1 mod kernel f is isomorphic to f of G1. So order of G1 mod kernel f is equal to order of f of G1. And f of G1 is a subgroup of G2, so order of f of G1 divides order of G2, and order of f of G1 divides order of G1 also. Okay, and since order of G1 and order of G2 is co-prime, that means order of f of G1 is equal to 1. This implies f is trivial. Okay. And second one is let G be a finite group and F from G to G a group homomorphism such that F fixes more than half elements of G, then F is identity. Okay, so let G equal to G1, G2 up to Gk plus 1, Gk plus 2, G2k, and say Gf fixes G1, G2 up to Gk plus t, where t greater or equal to 1, because we need that F fixes more than half of the elements of G, right? So it will fix at least k plus 1 element, right? Okay, now say we assume that F fixes this, and if F is not identity, let's assume that there is some element which F doesn't fix, right? So if F is not identity, choose X in G such that Fx equal to Y, where X not equal to Y, because F is not identity, right? So you can find some element which is not fixed by F. So Fx equal to Y, where X not equal to Y. Now F of X G1 equal to Y times F of G1, which is Y G1, because G1 is fixed under F. Similarly, F of X Gk plus T equal to Y times Gk plus T. Now see Y Gi not equal to X Gi, because since Y not equal to X, hence Y times Gi not equal to X times Gi for all I belongs to 1 up to Kt plus 1. That will imply that F doesn't fix at least K plus T element, which is a contradiction, because the total number of elements in G is 2k. If G doesn't fix at least K plus T element where T is greater or equal to 1, that means G fixes less than K elements, which is the contradiction for our given condition, right? Hence Fx equal to X for all X. Fx equal to X for all X. This will imply F is identity. Okay, move to the next option, that let G be any finite group having exactly 3 subgroups, then G is of P square for some P. Okay, so we need to use Shiloh's theorem here. So first of all, see that G has, okay, so it is better to start with some basic thing. See, if P and Q are primes such that PQ divides order of G, then G has at least 4 subgroups. G has at least 4 subgroups. Why? Because G identity, subgroup of order P, subgroup of order Q. And subgroup of order P and subgroup of order Q, that existence is ensured by Cauchy's theorem, right? We know that Cauchy's theorem, so that is ensured by Cauchy's theorem. Hence it is, we can think that G is a P group, because if there is at least 2 distinct prime divisors, then we have at least 4 subgroups. And since it is given that G has exactly 3 subgroups, so we can see that G is a P group, P power K, order of G. Now there is a basic result, maybe I will make a different video for this, that any P group has a subgroup of p power d for all d, any p group of order p power k has a subgroup of order p power d for all d less equal to k, right? So, and since it has exactly 3 subgroups, so d can be, so d is 0, 1 and 2, hence k has to be 2. So order of G must be p square. So third one is also correct. And fourth one, any finite abelian group G has at least d of order of G where dm divides number of positive divisors of m. So that directly follows from fundamental theorem of finitely generated abelian groups. In particular here it is finite abelian groups. So fundamental theorem of finite abelian groups. It will follow from this. How? So let n equal to p1 power k1 times p2 power k2 times pk power not pd power dk. Okay. Since G is abelian, G is isomorphic to its Shiloh-P subgroup. So I can write it as G is isomorphic to product of its Shiloh-P subgroups. So where HPI denotes the Shiloh-P subgroup of order pi power ki. It is kd pi power ki. Okay. Now say t be any divisor. Then t equal to p1 power m1, p2 power m2, pd power md, and since G is abelian, so G is isomorphic to hp1 cross up to hpd. Now from the previous theorem, previous result, we know that hpi has a subgroup of pi power mi. Then take that subgroup, say h pi comma pi power mi. This is the subgroup, and consider h as h equal to product of this, say hp1 comma p1 power m1 cross hp2 comma p2 power m2. This is just notation, cross hpd power pd power md, and order of h is d because order of h is product of order of h pi power pi times pi power mi, which is same as product of pi power mi I equal to 1 to d, which is same as p1 power m1 times p2 power m2 dot dot pd power md, which is d. So the last one is follows from directly from the finitely generated fundamental theorem of finitely generated abelian group. Here it is finite abelian group. Okay, hence all the 4 options are correct here. Okay, go to the next one. I think this one is very easy from ring theory if you know the definition. So it is saying that, see, fx equal to x square plus x plus 1 and gx equal to x square plus x minus 2. So first observe that in Z3 f of 1 equal to 0. That means f is reducible. F has a 0 over Z3. Right? Hence option 1 is wrong. F is reducible there because f has 0 over in Z3. Okay, second one is there exists a prime number p such that gx mod p is irreducible. But you can see that for any p, g of 1 is 0 because 1 square is 1 plus 1 minus 2 is 0. Hence g has root over zp for any p. Hence this is false. And gx is irreducible in qx. That is also false. Why? Because g has a root. root 1 in Q. Hence Gx is reducible. Fourth one is Fx is irreducible in Qx. That is true, because to check irreducibility of degree 2 or degree 3 polynomial over Q, it is enough to check whether it has any zero or not, right? So it is enough to check whether it has zero or not. And Fx equal to x square plus x plus 1, you can see that f has no zero in Q. Hence Fx is irreducible in Qx. This is the mod P irreducibility criteria, and in particular we are using mod P irreducibility. We don't want to use mod P irreducibility criteria here because we don't need to use this. You can just use that. So irreducibility of degree 2 and degree 3 polynomial over Q, it is enough to check whether it has zero or not. If it has no zero, that will imply that it is irreducible. Here we are using that. Okay, so now go to the next problem. So the next problem is saying that this is the last problem. The last problem says that okay, so the question ID 704086, that R is zx mod x square plus 1 and 5 from zx to R is the natural quotient map, then which of the following statement is true? Okay, so R equal to zx mod x square plus 1. So first define a map from zx to zi that any polynomial px goes to pr, p of I. Okay, and then by first isomorphism theorem, zx mod x square plus 1 is isomorphic to zi, because f is onto here, that you can show, because a plus bx goes to a plus bi. Okay, now it is easy to do all the options. So R is isomorphic to a subring of C, that is true because zi is a subring inside C. R has infinitely many prime ideals, that is true because zi has infinitely many prime ideals. And the ideal generated by phi x is a prime ideal in R. It is not true because ideal generated by phi x means ideal generated by phi x means ideal generated by I here, but I square equal to -1, which will imply that the ideal generated by phi x is in particular the whole ring R itself, because if I take this map, then that will becomes the whole zi, which is same as R. And for any prime p, the ideal generated by phi p is a proper ideal, because this is isomorphism, right? So this is the isomorphism zx mod x square plus 1, right? So psi p is the proper ideal inside R. So you can check that 1 doesn't belongs to the ideal generated by psi p for any p. Hence that is also false. So the main thing is in this question is that you need to see that zx mod x square plus 1, the ideal generated by x square plus 1, is isomorphic to zi. I think you all understand it. Thank you.